Welcome back to the deep dive. You've brought us something really interesting today. Less a problem to solve, more appreciating the beauty of physics, I suppose.
That's a good way to put it. We're looking at how electricity and magnetism, these forces we often think about separately, are fundamentally linked.
Right, through special relativity. You mentioned some source material showing that two key Maxwell equations, Gauss's law and the Ampère-Maxwell law, aren't really separate.
Exactly. They're actually just two different views of one single, much simpler equation written in 4 dimensions.
Okay, so that's our mission for this deep dive. Take these two, quite complex 3D equations about how charges and currents make fields.
And show how they're completely captured by this one tensor equation. Partial mu, that single line holds both of them.
It looks elegant, I'll give you that, but a bit intimidating too. You mentioned 4 dimensions.
Yes, that's the crucial first step. We have to stop thinking just about space, the 3 dimensions we walk around in. We need to think in space-time, 4 dimensions.
And that means treating time like another dimension.
Pretty much. We usually define the time coordinate, $6, as tick dollars. So time is measured in, well, the distance light travels.
Why do we need to do that?
It's essential for relativity. It makes the physics look the same no matter how you're moving. It puts time and space on sort of a more equal footing.
Yeah.
It's the natural language for electromagnetism once you bring relativity into the picture.
Okay, space-time framework adopted. Now, back to that equation. Partial mu commune. Let's break it down for you listening. What's hiding inside that field tensor?
Right, a $50. Think of it like a master container. It's a 4x4 matrix, but it's anti-symmetric, which is really important.
What does it contain?
It holds both the electric field, 5I lay, and the magnetic field, 5 del. All the components of both fields packaged together in one mathematical object. You don't need separate letters anymore in a fundamental sense.
You stressed it's anti-symmetric. So after mu, what does that tell us? Does that constraint do something important?
Oh, absolutely critical. Firstly, it immediately forces all the diagonal elements, like few dollar or EF7, to be in the row. Because, well, CL would have to equal E dollar, and only 0 does that.
Okay, diagonals are 0. Anything else?
Yes, more profoundly, it dictates how E and B are mixed together. The components that link time and space, the VI Lauder terms, they essentially are the electric field components, A di I.
Right.
And the components that link space to space, the phi I terms, they hold the magnetic field components, B I day, specifically phi I, var epsilon ij di I.
That epsilon is the Levi-Civita symbol, handling the cross-product nature of magnetism.
Precisely. And because of this structure and the anti-symmetry, if you look at, say, a purely electric field, but you start moving relative to it,
a magnetic field has to appear.
it must. It's not a new field appearing out of nowhere. It's just the same underlying field, being viewed from a different space-time perspective. The anti-symmetry locks them together.
Wow, okay. So the unification isn't just asserted, it's like built into the mathematical rules. That covers the field side. What about the other bit, Kano, the source vector?
If the fields are unified, then what creates them must also be unified, right? Canoe does that job.
So it combines the sources, charge and current.
Exactly. In 3D, we think of charge density, which is like static charge sitting somewhere, and current density, Caranu, which is charge flowing. Canoe treats them as parts of a single 4-dimensional current.
Ah, so charge density is like the time part of this 4 current, and the regular current is the space part.
You've got it. Specifically, the time component, Canolari, is built from the charge density. Kono, Ripsilon, we scale it by the permittivity of free space.
Okay.
And the spatial components for I1, 2, 3, they contain the 3D current density vector spawn, Xi. Again, there's a scaling factor involving C and epsilon naught.
So charge density arrays is just the 0 component. Current density arrays gives the spatial component. They're naturally part of 1, 4 vector.
Yeah, right. It's a unified source for the unified field.
Now for the payoff. We have the equation partial mu. You said it contains both Gauss's law and Ampère-Maxwell. How do we get them out? You mentioned using the index nowhere.
Yes, we essentially pick which component of the equation we want to look at using the free index. Let's start with the time component. We set no on dollars.
So the equation becomes partial mus k-mo d-rho 0, 0.
Correct. This equation should tell us something about, well, the time-like aspect of the field interaction. What does k-dollar represent again?
That was the charge density part, k-dollar for epsilon del. So this equation should connect the field to the static charges. Sounds like Gauss's law is coming.
Let's see if the math agrees. We need to expand the sum over the index. Remember, d runs from 0 to 3. So we have a u$ term, and then the mio run do 2, 3, 3 spatial terms.
Okay, the mind term is partial del, but wait, we already said has to be 0 because of antisymmetry?
Exactly. So that term, partial it just vanishes. It's 0. Gone. The structure of the tensor makes the first part simple.
That's neat. So the antisymmetry property is doing real work here, clearing the way.
It really is. So we're only left with the sum over the spatial indices, MUI, where all goes from 1 to 3. That's sommie partiale E.
And what was a partiale again? That was the electric field I.
Right. So we have a sommie partiale IA, which is just the sum of the partial derivatives of the electric field components with respect to their corresponding spatial coordinates.
That's the divergence. Nabla E.
Precisely. So the left side of the equation simplifies to $0 plus nabla EI.
And the right side was cdot E, which is frapsilano.
Put together.
Nabla E frapsilano, that's Gauss's law.
Bingo. Just by looking at the $1 component of that single tensor equation, Gauss's law falls right out. It's not just compatible, it's required by the structure.
That is genuinely impressive. Okay, so 1 down, 1 to go. Now we need the Ampère-Maxwell Law. That one involves currents and changing electric fields, creating magnetic fields.
So now we look at the spatial components of the main equation. We set new lie, where dollar can be 1, 2, or 3.
The equation is now partial mu kj. This feels like it's going to be more involved.
It is a bit messier, yeah. Again, we expand the sum over nueld, we split it into the time part and the spatial parts.
Let's take the time part first.
So
Partial f de Mahler.
What is antisymmetry again? A little bit of dollars and $5 was defined as E-half, the electric field component. So $5 and EJ.
Okay, and partial dollars is the time derivative, but scaled by $1. So partial dollars demands a frac $1.
Putting those together, the new old term becomes frac 1 partial t, for just frac 1 partial t.
Hold on. That frac partial term, isn't that Maxwell's big addition? The displacement current.
That's exactly what it is. Or rather, it's the term responsible for the displacement current in the final equation. It pops out naturally from the time derivative component in the 4D equation. It's not something tacked on. It's built in.
Incredible. The framework just demands it. Okay, that was the mu dollar part. Now the spatial sum, the mu dollar, that's sum UC SC Fij. This involves fate serine. Those are the magnetic field parts, right?
Yes. Phi J contains the components of the CB. This term requires a bit more vector calculus manipulation, involving that Levi-Acivitous symbol, for epsilon ijjt, for epsilon ijjg.
Okay, I'll trust the source material's derivation here. What does it simplify to?
It turns out that this sum, sommi partiale Faij, after working through the indices and vector identities, becomes Zeller times the jth component of the curl of the magnetic field. So C nobla times Bj.
The curl of B. That definitely belongs in the Ampère-Maxwell Law.
So now we assemble the full equation for the spatial component. We have the time derivative part and the spatial derivative part on the left, equaling the source term Kj on the right.
Let me try to piece that together. We had frac partial from the time part, plus defilo times Bj from the spatial part, and that equals Tj, which was repsilon jjj.
Perfect. That's the equation. Frac partial Ej plus Cj plus C, fractional C, Bj. It looks a bit punky with all the C's around.
Right. Needs tidying up. How do we get to the familiar form?
We want to isolate the curl of B, maybe multiply the whole thing by Z.
Let's try that. Multiplying by C gives for epsilon plus Cj2 frac 1.
Okay, getting closer. Now let's rearrange it to look like the standard law. Move the E field term to the right and maybe divide by 2/11 too.
Let's isolate the curl term first. So 2b lovas frac 1 Bj plus frac partial Jj plus frac partial Ej plus partial.
Now divide by 2jj, frac partial jj plus frac partial jj plus frac partial each duck 2 plus frac partial ej. Okay, this is where the magic happens. Remember the fundamental relationship involving the speed of light.
Ah, yes. $2 frac 1 μj. The speed of light comes from the permeability and permittivity of free space.
All right, so we substitute that in. Look at the term with the current, jj2 or c2. It has frac c2 var epsilon, then 2 var epsilon, then 2 dot, frac c2 var epsilon. So frac c2 epsilon is just number del hours.
Whoa, so that term becomes numbered jj2.
Nice, and the other term has frac onto 2, substituting 2 to part 2 gives var epsilon win, which is just a merb for epsilon.
So the second term becomes merged for epsilon frac per shol.
Exactly. Now put the whole equation back together for the GL component.
Nabla times Bj. That's the Ampère-Maxwell Law written for one component. Since this works for any J1, 1, 1, 2, 3, 3, it's the full vector equation.
Nabla times Bj plus mer epsilon frac per shol, derived directly from the spatial components of partial Mudersdu.
That's really quite something. So just to recap for everyone listening, we started with this single, compact, four-dimensional tensor equation.
Partial mood, By looking at its time component, we mathematically derived Gauss's law. Nabla e frapsilon.
And by looking at its spatial components, we derive the Ampère-Maxwell Law.
Nabla times b, j plus mother over epsilon frapsilon, both of them contained within the one original statement.
The takeaway here isn't just that it's, neat mathematical shorthand. It's deeper than that, isn't it?
Much deeper. It shows that special relativity requires this unification. Electric and magnetic fields aren't fundamentally distinct things. They are facets of a single entity, the electromagnetic field tensor now.
And how we perceive that entity, how much electric versus how much magnetic field we see, depends on our motion through spacetime.
Precisely. The way the fields mix and transform between observers is baked into the relativistic structure. The tensor equation works precisely because electromagnetism was already a relativistic theory, even before Einstein formulated relativity formally. Maxwell's equations had it hidden inside all along.
It's a testament to how fundamental these laws are. They fit perfectly into the spacetime structure.
Absolutely. The elegance isn't just aesthetic. It reflects the true nature of spacetime and fields.
So we've shown that this one equation, partial manu, covers half of the full set of Maxwell's equations, the two inhomogeneous ones, the ones that explicitly involve the sources, $2 and dollars, through to.
That's right. But there are two other Maxwell equations, Faraday's law of induction and Gauss's law for magnetism, the one that says there are no magnetic monopoles.
Those ones are called the homogeneous equations, right? Because they usually have zeros on the right-hand side. They describe how fields behave even away from sources.
Correct. They describe the intrinsic structure of the fields themselves, like how changing magnetic fields induce electric fields, or how magnetic field lines always form closed loops.
Which leads us to a final thought for you, our listener, to ponder. If this equation, partial mu so beautifully captures the source-dependent half of electromagnetism,
what equally elegant, equally concise four-dimensional equation might capture the other half? The source-free, homogeneous part. There must be one, right?
that seems like a natural question. What single tensor statement contains Faraday's law in the absence of magnetic monopoles? Something to think about.